So these three equations come under the category of exponential equations. These are considered exponential equations. So basically, you just solved three exponential equations, which we talked about earlier as not being possible until you learned logs. But you didn't have to use logs for these equations because of a very special property that you noticed. Like someone in my other class said, well, they're just easy, we can do these. And I said, okay, so what I'm trying to do is what made them easier for you? What was it about these equations that you could look at and get the answer so quickly? For at least for the first one. What is the reason, Clay? They're all perfectly raised. Well, they're not all perfectly raised, right? So I don't know how to say. I understand what you're trying to say. They're all perfectly raised. Which part is perfectly raised in this first equation when you say that? What do you mean by perfectly raised? It's raised to a all right. So 5 is raised to the power of x, and we're trying to solve for x. What can you do with 25 that makes this so easy to solve? No, we're not square rooting 25. What is the base of 25? Right now it's 25 to the first power, but what is it that makes this easy to do? Why can you do it? Because you can make it 5 squared, right? 25 can be expressed as 5 to a power, right? So you can take this equation and make it look like this. 5 to the x equals 5 to the second. So since you can write this equation as an equation that has exactly the same base, the only thing to solve here is to set your two exponents equal. So x has to equal 2 for these two things to be equal. So when you have the same bases, you just take your two exponents and set them equal. And there's no work to do here. If I had something like x plus 3 equal 2, then I'd have to solve that equation, but this equation's already done for you. X is 2. 5 to the x equals 5 to the second. It's done for you almost. And this next one, you have to do a little bit of work. You have 3 to the x on this side. And can you represent 1 over 81 as 3 to some power? So you can just set the exponents equal again. Can 1 over 81 be expressed as 3 to some power? What is it? -4, right. Again, your bases are exactly the same. There's really no work to do because there's your answer right there. X equals -4. When x is -4, 3 to the -4 equals 3 to the -4. All right. This next one you can do in a couple of different ways. I'm looking around to see, most of you got x equals -4. I'm looking for the work. Again, if you were to write this out with the work, there's a few different ways you could do it. 1/2 you could write this way. 2 to the -1. That's what 1/2 means. So if you substitute 2 to the -1 in there for a half, and then you write 16 so that you can express it as 2 to some power, it would be 2 to the 4th. So now you use your exponent property right here. When you raise a power to a power, you multiply your power. So you get 2 to the -1x equals 2 to the 4th. Notice again, you got the same exact base. So to make those equal, you set your two exponents equal. So -1x equals 4 means x is -4. So that one you actually had to do one step to solve the equation, whereas the other ones you were looking right at the answer once you expressed your base on the right-hand side to a power. Okay. Now, unfortunately, not all exponential equations can be done this way, because if they did, there probably wouldn't be too much problem in solving them, too many steps. You would just have to know your powers of different bases to solve it. So this particular method that we used here is a method that's called relating the bases. That's what your book calls it, relating the bases. You want to set your bases so that they're equal. You make the relationship of equality between your two bases, and then you just look at your two exponents. and solve for x. So as you just noticed, you can all do that pretty as a straightforward problem. All right. So let's take a look at a situation where it may not be that straightforward and see what we do. So an exponential equation is exactly like it sounds. It's an equation where you have an exponent that's a variable. So right here is an exponential equation. Okay. And just like all equations, every time we want to solve an equation, we want to isolate the expression that has your variable in it. So in this particular case, it's called an exponential expression because we want to isolate all by itself 5 to the x power. We want to get that all by itself on one side of the equation. So to do that, how would I undo this? What would be the first step here to get that 5 to the x all by itself? What would I do? Taylor? Divide 50 by 2. I would divide both sides of the equation by 2, right? Because I'm undoing the multiplication of 2 that's right there in front of 5 to the x. So divide both sides of the equation by 2. We solve equations by inverse operations. So we're going to divide this by 2, and we're going to divide this by 2. And we get 5 to the x equals 25. Well, we just did this problem for the preview exercises. So if we use the method relating the bases, which we can here, because we can express 25 as 5 to the second, then we know x is 2. But we're now at the point where we want to look at another method that will always work, whereas relating the bases only works in a situation like this. So what method will always work? Well, we want to undo exponentiation. We have to find the inverse of exponentiation, which is to take the logarithm of both sides. Now, it doesn't matter what log you take. You could take log of any base in the world, any real number, as long as it's positive. Because remember, our domain for a log function is all positive numbers. However, your calculator only gives you the answers for the common log and the natural log. So I'm just going to follow what your book does. Your book has this like love affair with the natural log. It takes the natural log of both sides of the equation. So we're going to take the natural log. What we have to do is, this x up here is feeling high and mighty, and we want to bring x down to earth. Okay, we want to be able to solve for x. And the only way to bring this down to earth is to undo the exponentiation with the log. So I'm going to take the log, natural log of both sides. So I'm going to put natural log in there, and then I'm just going to write that right in front of each thing that I have here. Natural log of 25. Okay. Now, these bases are not the same. The base of 5 to the x is 5. The base of the natural log is e. So I'm not composing inverse functions here. But what I can do is I can use my log property that says when I have a power to a power, my x comes down in front. That's how I'm going to get it out of the air, so to speak. I'm going to bring it right down in front using my log property. X comes down in front, and it multiplies the natural log of 5. And on this side, I have the natural log of 25. So I'm almost done. I've got my x where I want it. Now I just have to isolate it. I want to undo multiplying by the natural log of 5. Before I do that, I want you to see something. I want you to look at this thing right here. Look at it. Oops, it's supposed to be eyeballs. And look at this. I want you to look at those things and not get all freaked out because you see natural log of a number. It's just a number. Natural log of 5 is a constant. Just as if this said 4 times x equals 24. These are just constants. So to undo the multiplication of x by the natural log of 5, to undo multiplication, you divide by whatever this number is. This number is called the natural log of 5. I don't have to put it in my calculator. I just divide by the natural log of 5 on both sides. So I divide this by the natural log of 5, and I divide this by the natural log of 5. This gives me a 1. The natural log of 5 divided by itself will always be 1. So on the left-hand side, I have x all by itself. And on the right-hand side, I have the natural log of 25 divided by the natural log of 5. Those are two different numbers. The only way you can get your answer, there's two ways to do it. One is to pull out your calculator and just do the division on your calculator. And then I can show you another way that came up in my previous class. So let's turn the calculator on. We take the natural log of, we already know the answer here has to be 2 because we've done it by relating the bases. Divided by the natural log of 5 is 2. So x equals 2. Now, another way that you probably wouldn't think of, and why would you, but it came up in my other class, is someone in my other class wrote 25 like this. And then they used their property where they bring the exponent down in front, 2 times the natural log of 5 divided by the natural log of 5. And there's another big one right there. And they got the answer 2 that way. So just like when you have to simplify exponent properties that involve lots of different properties, sometimes you can simplify these log equations, or these exponential equations, in more than one way. The point here is you can just use your calculator to do that division. Okay. Any questions on this problem before we move on to another problem? Any questions? All right, let's try the next one. Do I have another one before this next one? Is it down here somewhere? Oh, it said to check my solution, so I better go back and check it. So to check my solution, it says 2 times 5 to the x equals 50, right? So I substitute the number 2 for x and see if my left side equals my right side. 2 times 25. Does that equal 50? 50 equals 50, so I'm a happy camper. All set. All right, so the next problem on this goes to a different type of equation. Really? Is that all I have here? One? Oh no, there is one. I'm missing one here. Yeah, I'm looking for that. Yeah. Oh, here it is. Okay. All right. So I didn't lose it. Okay, so that was an example of how to solve an exponential equation. Now let's take a look at a logarithmic equation. And sometimes you think, oh my God, logarithmic equations, they must be harder than exponential equations, but they're not. They're actually easier because you can take every log equation and turn it into an exponential equation. That helps you find your answer pretty quickly. So our goal to solving a log equation is to convert it to an equivalent but easier to solve exponential equation. Sometimes you need to use a log property to help you manipulate the log equation first. But if we take a look at this equation, you know you want to solve for x, and just like you always want to do, you want to isolate your expression with the log in it. That means you just want to have log 5x all by itself. So how are you going to undo the multiplication of 2? How do you undo that 2 in front? Divide, right. So you're going to divide both sides by 2. So you do that, you divide both sides by 2, and you get log 5x equals 2. Now the next step is the critical step, and this is why solving log problems, they can be so easy. Most of you are not going to exponentiate both sides and raise this 10 to this power and 10 to that power. You're not going to use that property that we looked at when you compose two inverse functions. You could exponentiate both sides by base 10. But what's easier to do is to say, okay, here's a log problem. Can you tell me what the base is of this log? The base of the log is my question. What's the base? You don't see it looking at you, right? You can't see the base, so what's it understood to be? 10. That's called the common log. So even though it's not there, there's the 10. The 10 is hiding right in there. Okay? So if I want to make this into an exponential equation, I need a base to a power equals some answer. Okay? To make that into an exponential, I need a base to some power equals some answer. So I've got to look at all of this equation here and figure out how I make it look like an exponential equation. One part comes out really quickly. Once you determine the base of your log, it's exactly the same as the base for your exponential equation. So right away, I can put the 10 in there. Melanie? Sure. Because it just says log, Melanie. Anytime a log is written without a number here, it's understood to be 10. We call that the common log. Okay, you're welcome. Okay, so 1/3 of the way home now. I've got 3 spots to fill in here in my exponential equation, and I've got 1 spot filled in. 10 to what power is equal to what? Well, remember, a log is an exponent. So the answer to the log is your exponent. This is your exponent. It comes right down here. And then your input for your log is the output for your exponential function because they're inverse functions. So this is 5x. So if I were looking at this exponential function, 10 to the x, I would put 2 in and 100 would come out. When I look at its inverse function, I put 100 in and out would come 2. And notice this is 100 right here. So now you have an exponential equation to solve. It's very simple. 10 squared is 100. 100 is 5x. You solve for x by dividing both sides by x, by 5, and you get 20. Voila, you're all done. Now you check. So let's do our check. I put my answer in. 2 times the log of 5 times 20 is supposed to equal 4. Well, let's see. 2 times the common log of 100 is 4. And Melanie, because this has a 10 hidden here, 10 to what power gives me 100? 2. 2 times 2 is 4. 4 equals 4. You're all set. Okay. So when you have a log equation, you isolate your log, and then you just write an equivalent exponential equation, and it gets solved pretty straightforwardly. Okay. Any questions on that? Sure. Yep. Yep. Okay, let's take a look at the next problem. Okay, so sometimes we have to use our log properties in order to isolate our log. Now, when I copied this over to SmartPrint, I missed out on the last property here, which is log base B. What does it say on your paper? U to the R? U to the R. Okay, thank you. U to the R log base B. All right. And that's called the power rule for logarithms. Okay, so when I converted this over, we missed. But these are the 3 properties that we worked on last week. And we talked about its relationship to the exponent properties. When we're multiplying 2 exponential expressions with the same base, we add the exponents. Here we have the product of the log of base B of a product. We add the individual factors, log base B of U plus log base B of V. Both of these represent exponents, so we're adding the exponents. When we divide, we subtract exponents. When we raise to a power, we multiply the 2 exponents. So these are very similar to properties of exponents that hopefully you have some comfort with. Okay. So now you see we have a little dilemma here because we have a log equation, but we have logs on both sides of our equation. So in order to isolate this, we have to, first of all, to isolate a log means you have one log. Right now we have two logs. So the first thing we have to do here is get all our log terms on the same side. And it doesn't matter which side you bring it to. So I'm going to add log base 2 of x to both sides. Add log base 2 of x to both sides. And just out of habit, I always put my input into a log in parentheses. Okay, that's just my habit. Okay, once I do that, my new equation gives me a 2 on the left side. And now I have log base 2 of 4x plus log base 2 of x. So when I look at that right side, I say, oh, both of my logs have the same base. They both have the base 2. I'm adding logs, which means I can combine that now to a single log using my log property, my product rule. So I can call this 2 equals log base 2 of 4x times x. I can just multiply those two, 4x and x. Now I can call that 4x squared. So all I did here was use my log property, so I have one logarithmic expression on my right side. Now I have a single log. How do I undo it? Well, I can rewrite this as an equivalent exponential equation. All right, to have an exponential equation, I need some base. I suppose I should make that look like home base, right? Home base to some power equals an answer. So what's my home base here? 2, because the base of my log and the base of the equivalent exponential function must be the same. My power is the log. My power is the log. Here's my log. What is my log equal to? 2. So 2 to the 2. And my answer here, the answer to my exponential equation is the input from my log equation, 4x squared. So now I solve this equation, which can be done in fairly quickly. 4 equals 4x squared. I divide both sides by 4. I get 1 equals x squared. So I have a little baby quadratic equation to solve. So I get x squared take away 1 equals 0. Most of you will just square root, extract roots from both sides, but that often leads you to forgetting one of your answers. So I always like to factor. X plus 1, x minus 1 is 0. So the question is, do I have two answers here? Can x equal -1 and can x equal 1? Well, in order to find out, I better check both of these answers. Before I do that, let's take a look at a graph of a log. Here's a common log. A common log always goes through, not common log, excuse me. I can't say common because common log means base 10, but what I want to say is this is a generic log. Generic. And remember, on a generic log, you always have the point b comma 1. So once you find that point, b, whatever the x value is when y is 1, that's the base of your log. But a parent log, yeah, it could be a parent log. There you go. Yeah, parent function, right. Generic, right. So in this case, what I want you to notice is what's the domain for any parent log function that has this form? What's the domain? Do you see your graph over here with negative numbers? No. Your domain is the values of x. 0 to infinity, and what do I use for interval notation here? parentheses, right? We can't be 0 because there's no way I can take the log of 0 because 10 or 5, there's no number you can raise a base to get 0. Just like your exponential function, which is its inverse, can never have 0 as an output. These are, remember, inverses of each other. So the range for your exponential function is 0 to infinity. So the range for your exponential becomes the domain for your log. So you can never take the log of a negative number. It's not possible. So what we have to do is go back and see where this -1 fits into our original equation to see if I'm adding 2 to, if I'm taking log of x plus 2, then it's all right to substitute -1 because then it would be log of 1. But I have to look at my original equation. What's my original equation say? 2 take away log base 2 of x equals what? Log base 2 of 4x. So I'm going to check, first I'm going to check 1. Let's check 1. 2 take away log of 1, does that equal log of 2 times 4 times 1? Well, let's see. What's log of 1 regardless of the base? Nope. 0. Any number raised to the 0 power gives you 1. And this is log base 2 of 4. So this is 2 equals 2. So 1 is an answer. That works. Now let's check out -1. 2 minus log of -1. The minute I write that -1 in there, no go. So I can't take the log of -1. It doesn't exist. It's not in my domain. Now, if that had said log of x plus 2, I would have been fine. Because when I add -1 and 2, I would have gotten 1. But it doesn't. It just says log of whatever your x is. So the only answer here is 1. So this would be what we call extraneous, just like when we're solving equations where we get a number that doesn't work. Okay, like our radical equations. Any questions on that? Going from the log to the exponential. Now, all your class activities, I'm going to be leading you through some new types of problems, but I'm going to give you the steps. Clay? Yep. Yes. That way you actually get just the one answer that works. You don't get the quadratic. Okay? So that's just a different approach using your properties. I didn't even turn, you see what I did? Okay. Okay. So as with simplifying exponential expressions, you can often do these a couple of different ways. All right, let's see what's coming up next, if anything. Woohoo! Class activities are coming up. Woohoo! Right? So you have 34 minutes. You should be able to get through all the class activities. It's awful.